Hello students. So today I'm going to talk to you guys about exponential functions. Now, an exponential function is a nonlinear function in the form y equals ab to the power of x, where a cannot be 0 and b cannot be 1, and b has to be greater than 0. Now, one thing that's important about exponential functions, something important to note, is that as the x changes by a constant amount, the y is multiplied by a constant factor, okay? So, and what happens, something that a key feature in an exponential function is something called an asymptote. An asymptote is a line that the graph approaches but never actually intersects. Now, if you have a function in the form y equals ab to the power of x, the a value is the initial value, also known as the y-intercept. The b value is the constant ratio, okay? Now on the test, we might ask you what these values mean. So there it is. Your a value is the initial value or the y-intercept. The b value is the constant ratio. Now, exponential functions are pretty dramatic. Take, for example, f of x equals 2 to the power of x. So if we have f of x, 2 to the power of x, and I made a table, let's say that I want to plug in these values. If I plug in -2 in for x, that's the same as saying 2 to the power of -2. That is the same as saying, you know, from what we learned about laws of exponents, 2 over 2 to the power of 2, which is the same as 1/4, right? If we plugged in 1/2, we would get 1 over 2 to the power of 1, which is the same as 1 over 2, or 1/2. If I plugged in 0, 2 to the power of 0, anything to the power of 0 is just 1. 2 to the power of 1 is just 2. 2 to the power of 2 is 4. 2 to the power of 3 is 8. And 2 to the power of 4 is 16. Notice how fast it grows. It starts off at a pretty small number, 0.25 or 1/4, and then it goes to a less small number, 1/2, and then it goes to 1 and 2, and then it starts growing exponentially. From 2, it goes to 4, and then from 4 it jumps to 8, and from 8 it jumps to 16. And if you continue plotting larger numbers, it's going to increase exponentially, which is why it's called an exponential function. So let's see how this looks graphically. If I was to graph -2 1/4, that's really close to 0. Would you agree? Super close to 0, somewhere there. That's actually not a 100% accurate image, but you get it. At -1, we have 1/2, so it's a little bit larger, but not really. And then at 0, it's at 1. And then at 1, it's at 2. At 2, it's at 4. At 3, it's at 8, which is up here, I think. And then at 4, it's at 16, which is like all the way up here somewhere. Now, notice this. If I was to graph this, as I get to more and more negative numbers, it gets really close to 0, but it never actually approaches 0. All right, think about it. If you have a number and you're multiplying it by, let's say that you're halving it or whatever. So if we were to continue to get these smaller numbers, you're just going to get to a smaller fraction. It's just going to keep dividing by a smaller fraction, right? But it's never actually going to get to 0. So it approaches 0, but it never actually touches 0. So where it approaches, where the graph kind of flattens out, that's where your asymptote is. So in order to draw the asymptote, I'm going to draw it in a different color. You're just going to draw a dotted line at where it flattens out, right? So it flattens out at the x-axis, and most of the time that's where it flattens out, unless there's some type of transformation. Okay, so now let's think about the domain and range here. If we look at the range, or let's look at the domain first. The domain here, we always read the domain from left to right, is all real numbers, right? So if we look at the negative infinity side, that goes on forever. If we look at the positive infinity side, that goes on forever. So then the domain would be all real numbers. Now, the range is a little bit different. So the range, the y values, we start off at 0, but it doesn't actually ever touch 0 since 0 doesn't actually exist. So the range here would be y is greater than 0. So it's all the y values that exist that are greater than 0, right? Because once again, nothing actually exists at the asymptote. So that would be how you would kind of graph this. Okay, so when graphing an exponential function, you have two things. You have a and b, right? We kind of already discussed that a is your y-intercept and b is your constant ratio, right? So if your a value is positive, it's going to be kind of on the top half of the graph, right? It's positive. If it's negative, you would flip it about the x-axis, and so then it would be negative, right? Now the b value tells you whether it is increasing exponentially or whether it is decreasing exponentially, right? So if the b value was greater than 1, then that means that it would be increasing exponentially from left to right, right? And that's considering that the a value is positive. If the a value is negative, then you would simply flip it about the x-axis, and so then from left to right, it would be decreasing. If you have y equals ab to the power of x, where b is between 0 and 1, right? So that means it's like a fraction. So you're basically like, for example, 1/2. So if you're multiplying something by 1/2 each time, obviously your graph is getting exponentially smaller, right? So if you were to read it from left to right, your graph is decreasing from left to right. And then obviously if the a value is negative, then you would just flip it about the x-axis. So then it would look like this, give or take. So here they ask us to determine whether the table represents a linear or exponential function. Now we said earlier that if a function is exponential, then as the x changes by a constant amount, the y is multiplied by a constant ratio. All right, so let's first determine on question 1. So my x values, they are changing by a constant amount, right? By +1, +1, +1, right? But over here, they are in fact being multiplied by a constant ratio. So if we go from 8 to 4, that's being multiplied by 1/2. From 4 to 2, that's being multiplied by 1/2. And from 2 to 1, that's being multiplied by 1/2. Since it's being multiplied by the same exact constant, then, or by the same exact ratio rather, then we know that this is in fact an exponential function. Alright, so I'm not really sure what happened to this graph, but the 11, the 1 was cut off of the 11 and the 5 was cut off of the 15, so please just include that in your notes. So anyways, if we look at this particular graph, we notice that the x values are changing by a constant of 1, and then my y values they're not being multiplied by a ratio, right? In fact, instead they're actually being added. So there's a constant being added. There's a number being added constantly. So 3, to get from 3 to 7, they added 4. To get from 7 to 11, they added 4. And to get from 11 to 15, you have to add 4. So this would be a linear function because you're not multiplying by a ratio. Okay, so if we look at this next one, we have, it is being changed, my x values are being changed by a constant amount. So from -1 to 0, that's +1. From 0 to 1, that's +1. And from 1 to 2, that's +1. If we're looking at the y values, from 12 to 9, they are subtracting 3. From 9 to 6, they're subtracting 3, and from 6 to 3, they're subtracting 3, right? So once again, since we're not multiplying by a ratio, this would be considered linear. If we look at this next one, On question 4, my x values once again are changing by a constant amount, so we're adding 1 each time. And then over here, oh, that's weird. Sorry guys, had to fix that. That should say 0.5. So from 0.125 to 0.5, you're multiplying 4. From 0.5 to 2, again, you're multiplying 4. And from 2 to 8, again, you're multiplying 4. So because you are multiplying by a constant ratio each time, this would be, in fact, an exponential function. Okay, on question 5 and 6, it says compare the graph to the graph of the parent function, identify the y-intercepts and the asymptotes of the graph, describe the domain and range of f. So for these questions, you can either graph them on your calculator or you can make a t-table. I'm going to go ahead and make a t-table here and just graph the points. So on question 5, I'm going to use the numbers -3, -2, -1, 0, and 1, and then I'll just plug those values in to my x value. So if I was to plug in -3, I would get -0.125. If I was to plug in -2, I would get -0.25. If I was to plug in -1, I would get -0.5. If I was to plug in 0, I'd get -1. And if I was to plug in 1, I would get -2. So if I was to graph this, at -3, I have -0.21. So super close to 0. And then at -2, I have -0.25. So that's a little bit further away, but still pretty close to 0. And then at -1, it's at -0.5. Once again, we're kind of getting further and further away from 0 here. At 0, I have -1, and then at 1, I have -2. So my graph sort of looks like this. Ooh, it's a really bad graph. But it looks something like that, and it kind of flattens out at the 0. So now I'm going to draw my, my horizontal asymptote at 0, since that is where it flattens out. And it asks us to identify the y-intercept. So the y-intercept, if you look at the graph, is at -1. And the reason it's at -1 is because my a value is -1, right? So therefore my y-intercept is -1. My horizontal asymptote is y equals 0. And then now looking at the domain and range, the domain is all real numbers, and then the range would be y is less than 0, because nothing actually exists at 0 since we have an asymptote there, but all the values below that exist. If you wanted to graph this on your calculator, you would go to Menu, Graph, and then you would plug in -2 to the power of x, hit execute, and then to identify the y-intercept, you would do Shift G solve and then y-intercept, and they will give you that the y-intercept is -1. For the horizontal asymptote, there's no way to actually find that using your calculator. You just kind of have to look at where it flattens out, and that would be your asymptote. And you can see clearly on your graph, if you're graphing it right now, that it does flatten out at the x-axis. And then again, the domain and range, you would just have to look at that and kind of see. So let's look at question 6. If I was to choose some random points on question 6, I'm going to choose the points -1, 0, 1, 2, and 3. So if I was to plug in -1, I would get 8. If I was to plug in 0, 2, if I was to plug in 1, I have 0.5. If I was to plug in 2, I have 0.125. And if I was to plug in 3, I have 0.0312. Okay, so we are getting really, really small there. Okay, so at -1, it's at 8. It's not even on my graph, so it's kind of all the way up here-ish somewhere. And then at 0, it's at, it's at 2, at 2, it's at, at 1, it's at 0.5, so now we're getting really close to 0. At 2, it's at 0.125, so super close to 0, and at 3, it's like so close to 0 that I can't even draw that. Alright, so if I was to draw this out, it would look something like that, where it kind of flattens out at 0. Alright, and then I would have to draw my horizontal asymptote. I'm going to use a different color there at my x-axis. Okay, alright, so my y-intercept is at 2 because my a value is at 2, and again, you can use your calculator to double check. You could do shift G solve and then y-intercept. So my y-intercept is at 2. My horizontal asymptote is at 0, so that would be y equals 0. The line y equals 0, it's at my my x-axis. That would be my asymptote. That's where it flattens out. My domain, in this case, is all real numbers, and my range, once again, it flattens out at 0, so 0 doesn't actually exist, but all the numbers above that exist, so then it would be y is greater than 0. Okay, so for this next part, we have some transformations involved. So in exercises 7 and 8, actually, that should say, graph the function and identify the asymptote. Describe the domain and range. So I'm actually going to give you guys a little bit of time to graph this on your calculators. So go ahead and pause this video and graph it on your calculator. Alright, so if you were to graph this function, you would have gotten something that looks a little bit like this. Now, as you notice, the horizontal asymptote is no longer at the x-axis. So now my y-intercept is at -2. The reason for that is because this -2 here tells us that this entire graph moved down 2 units. So you guys should kind of already know that from transformations. So my new y-intercept, or my new horizontal asymptote, let's just call it HA, is y equals -2. My new y-intercept is now at -1. Okay, so originally it would have been at 1 since my a value is 1, but since we moved everything down 2 units, now my y-intercept is at -1, right? Because, 1 minus 2 is -1. My domain, again, that doesn't really change because all my x values do exist. So my domain is all real numbers, and my range, that does change. So my range would be all my values that exist above 2. So y is greater than 2. Go ahead and pause this video and graph question 8. Okay, so when you graph this on your calculator, you should have gotten something similar to this. Alright, so now you notice that this time your translation is next to the x, right? So it's in the exponent. Now what happens here, what this basically means is that this entire graph shifted to the left 1 unit, alright? So how does this affect my graph? Well, if I look at the horizontal asymptote, that doesn't change. My horizontal asymptote does not change, right? Because we're not moving this thing up or down. So my horizontal asymptote is still y equals 0. My y-intercept, that does actually change. So my new y-intercept, and again, you can find this by doing shift G solve y-intercept, that's actually at 2. All right. My domain doesn't change, right? Because my x values all exist. So my domain is all real numbers. For my range, that also does not change since my horizontal asymptote does not change. So my range is still going to be y is greater than 0. Okay, go ahead and graph question 9. Graph both f of x equals 2x and graph g of x equals 2x plus 3 on your calculator. I want you to show both of those on the first 2 lines and then compare them. I'm going to go ahead and pause this video so that you can. After graphing these two functions, you can see that the entire function moved up 3 units. So the domain here doesn't change because my x values all exist. However, my y-intercept and my range have been affected. So my range, where it used to be y is greater than 1, is now y is greater than 4 since everything moved up 3 units. My y-intercept, it used to be at 1, right, because my a value is 1, but then since everything translated up 3 units, it is now 4. So this basically sums up everything that happened. Okay, so this last question says, if a rubber ball is dropped from a height of 10 feet, the function f of x equals 0.6 to the power of x gives the height in feet of each bounce where x is the bounce number. What will the height be after the 5th bounce? Round to the nearest 10th. Okay, so this is pretty simple. So we have f of x equals 0.6 to the power of x, right? Now we know that this is going to be decreasing since my b value is between 0 and 1. It's decreasing the height after each bounce. Now we want to figure out the height after the 5th bounce. So the way that you would do that is you would plug in 5 in for x, since we know that x is the bounce number. So we would do f of x equals 0.6 to the power of 5, and you would just put that in your calculator. So f of 5 equals, and this actually should have said f of 5. So if you plug this into the calculator, you get 0.077 repeating, which they said round to the nearest 10th, so that would be approximately 0.1 feet.